Well, hello everybody, and welcome back to our next series in the ultrasound, ultrasound. You can tell what I've been working on over the last few days. Oscilloscope series. I want to start this out. Originally, we were going to start on some of the newer type scopes, but I had a really fantastic comment from one of the viewers, and he had brought up something that I had not mentioned to you guys that's really very important. So I want to thank him for making that comment. And that comment deals with these knobs here. We talked about the volts per division for the vertical scale and the seconds per division for the horizontal scale, and that's all well and fine. And we talked about how we can use those two knobs to set the graticules and actually make accurate measurements. So we saw on the last video how we can actually measure the time period and the frequency of a waveform, and we also showed how we could measure the amplitude of the waveform with the volts per division. But there is one very important thing you have to remember, and that is, if you look on these big knobs, in the front of them is a smaller knob, and this knob actually rotates, okay? And you notice it says VAR, V-A-R, and channel 1, channel 2, and even your seconds per division, all three have those knobs. And if you rotate the knob, it clicks. If you turn it all the way clockwise, it will click into a detent. Now, what that means is when it's clicked all the way to the right, then the volts per division and seconds per division are calibrated. They are accurate. In other words, when we look at the, let's change this intensity so we can see it on the screen better, so it's not so super bright. There you go. When it says 500 millivolts per division and 2 microseconds per division, that's truly what they are. Now, however, I can unclick these by turning them counterclockwise, and what you're going to see is that it is going, let's see, for instance, the seconds per division. If I rotate that knob, let me get you zoomed in here. If I rotate that knob, see what happens? It scrunches the image tighter together. So what that does is, let's say this position is too wide and this position is too narrow, and I want to change the actual, I'm more interested in looking at the whole waveform than I am at measuring the waveform. I can use those are variable adjustments, and I can vary to a certain degree my volts per division. Now, it's no longer accurate, even though this oscilloscope knows where it is and it's actually technically calibrated still. A lot of scopes won't do this. They won't give you the actual scale as you adjust it, especially the lower end scopes. But I can scrunch this down to see the waveform a little more clearly, and fit it onto one screen. So let's say I was looking at something like this and I wanted to be able to see the whole waveform and fill up the whole screen. Well, I can do that. I can turn this variable adjustment, and I could bring this just so now you can see I have one whole waveform in there, okay? Or one whole cycle. So it's handy for that. But you just have to remember, if you want this thing to be calibrated accurately, you want these to be clicked into their full calibrated position. And likewise goes for the vertical. So see how my vertical is off scale right now? Well, I go this far and that scrunches it down a whole lot. If I want to be able to really see the whole thing in one screen, I can adjust it ever so slightly and fit it into one screen. And that's the purpose of those variable adjustments. So I just thought I would, before we move on to the next lesson here, I wanted to do that little addendum to the last video that we did. Good catch on that, because that's actually very important. If this thing's accidentally rotated and you're counting divisions per second, and instead of having an on-screen display, it has a display that involves, that shows the little graticules, on the knob. Because some of the lower-end scopes, the knob will have a little pointer on it, and as you rotate that knob, for the volts and the seconds, the knob points at the scale that it's going to be. It doesn't show up digitally on the screen. This is a little bit fancier scope. Okay, so you may buy one that does not have that. For instance, I don't think the Tektronix 465s have that. They have the graticules marked on the knobs, or the scale marked on the knobs. Okay, so just something for you to keep in mind. And now we're going to move on to our next part in this series. Okay, so let me get things rearranged here, and we'll be right back. Okay. What we have in front of us now is another Tektronix oscilloscope, and this is the model TDS3032, and the reason we're focusing on this one is this is what I'm going to call a fully digital oscilloscope. Okay, and the word digital can be used in different contexts when it comes to oscilloscopes, but for all intents and purposes, let's just say that this is what I would consider a modern oscilloscope. Now, this scope is probably, this model is probably 10 years old or so, maybe. They've been around for that long. But even the new versions of this are very, very similar to it, okay? And the reason that I'm going to call this digital, of course, Tektronix has a kind of their marketing thing. They call it digital phosphor. Really, it's an LCD or LED display, but it's very high resolution. Let's talk a little bit about these newer scopes. Okay, the first thing you'll notice about these scopes is they're very thin. Okay, so if I take this out of the holder here for a second, you can see these scopes are very, very thin when you compare them to the original, some of the older ones, like that 2467 we were looking at. That 2467 is probably, 18, 20 inches deep. Very large case, big, heavy scope. This is a little plastic case. It's very lightweight, maybe 5 pounds, if that. But still a very expensive oscilloscope. This one is. It's a 300 megahertz. But anyways, this scope does not have a CRT, or a cathode ray tube, for the display. This has an LCD or LED display that's similar to some of the higher end cell phones that you'd see today, and things like, or your high resolution televisions and monitors on your computer and things like that. So of course an LCD or LED display is very, very thin compared to a CRT, very, very lightweight. Obviously it's a color display instead of a monochrome display. This one in particular has a very fast response time, so it can mimic a CRT, but there are differences, and these are some of the things I want to talk to you about right now before we get really into the functionality of this scope and how to use it. Some of the things you need to know. I want you to understand the different types of scopes so that when you make your choice to purchase a new scope, you're going to make the correct choice. And again, I'm not going to endorse or talk down any one type of oscilloscope, because really it just depends on what you want to do as to what will be sufficient. The other thing is the budget that you're on, how much you want to spend. Many, many different factors come into play, in my opinion, when you want to talk about choosing your first oscilloscope. And so I just want to give you all the pros and cons of everything. So On our 2467 and on the older scopes, the CRT based oscilloscopes like this one, you have a cathode ray tube, and you got to see what one of those looked like when we were inside that the DeVry Institute vacuum tube oscilloscope. Okay, of course the CRT in my Tektronix scopes here are a much higher order of CRT. They're much higher quality, more advanced technology, but it's still a picture tube. It's a monochrome picture tube, sort of. And the advantage of those is the way the phosphors are designed and the way that those picture tubes are designed. They have a very, very fast response time, very low lag. Now, what's lag? Lag is a term we refer to when we talk about the time that it takes for that phosphor, when that electron beam strikes the phosphor, how long it takes for it to light up, and then how much time it takes for it to extinguish again once it's been lit up. And a high-end oscilloscope that's very expensive with a CRT has a very, very low lag and very high response time, or quick response time, for that electron beam and for that phosphor. And that's why you can see that really crisp looking image on that screen. If you tried to do that on a picture tube for an old television, it would be fuzzy and laggy, and it wouldn't look, you wouldn't have that beautiful, sharp, bright trace that you saw when we were looking at the last video. Okay, even the CRT in that DeVry oscilloscope is faster and more responsive than a CRT in a television. Okay, so that's one of the things. Now, why am I going through all this? Well, these types of scopes, which are the newer ones, and you can see behind it is another scope we're going to look at last, which is a low-cost modern oscilloscope. But it shares a lot of the technology and a lot of the functionality of the better quality, more expensive scope. And the thing with them is the earlier models of these, you can buy these that are older ones, and you can also buy really, really inexpensive ones. They have little kits of little handheld oscilloscope kits. They're $20 or so you can buy, but they use a standard LCD display. What's the problem with an LCD? Well, an LCD inherently, by design, just the way they are, have a lower lag than a CRT. Now, we've definitely come a long way with that technology. This digital phosphor scope has a very fast response time, even though it's an LCD display or an LED, whatever you want to call it. And that's part of the reason why these scopes cost so much and why they're more expensive. If you purchase the lower cost ones, some of them will have a slower response, like more of a television type display on them. And when you start looking at really high frequency waveforms, you'll see that they start to get a little bit blurry, or they get a little bit like smeary. The image smears a little bit, and that's because of the display itself is not able to refresh that image enough times to make that image stay nice and clear. So that's one of the things you want to think about when you're going to buy one of these newer modern type oscilloscopes, that do not have an actual CRT in them. Now, one of the positives of them is this is so much more than just a display for a waveform. If I go into a menu, look what happens here. These modern scopes have on-screen displays and on-screen programming. So this is one of the advantages, that this works almost like, this is really a computer. It really is. You're looking at a computer, and this is the monitor, and it's a very high, we talk about gaming monitors versus, standard monitors for computers, and, games always, the graphics of a video game are so fast. You have to have a really fast response time monitor display. That's what these are. And so it allows you to do a whole lot of functions that you did not have, or that you would have had a physical button for on the older style scopes. So if you look, there's relatively few buttons on this oscilloscope when you really consider what all this scope can do. This can do, much, much, much more than the 2467. Now, when we're talking about just looking at a waveform, they're the same. They both look at a waveform, they both do a beautiful job of it. But when you start about advanced functions like math and advanced display functions, this scope can do just, tons more than that other one. So we'll get a little bit more into that as we go through this video. So you have the flat display, you have the smaller case, it's lighter weight, it's got more of a computer in it. This other one, these other scopes had some firmware in them, some software. The older ones did not. They were all analog. But by and large, this is still an analog oscilloscope with some digital overlay for the display. So you could see like the volts per division, it has some text. It can do basic measurements and put them up there. But this is so much different. Now, one of the things you have to really think about with these scopes is the way they work internally is much different from the way an old analog oscilloscope works. If you look at our first video, the DeVry, and our second video, you saw very distinct analog circuits in there. You saw an oscillator, ramp generator that created your horizontal sweep. You had a vertical amplifier that would take the signal coming into it and amplify it and turn it into a deflection on the CRT. Everything was analog and it made total sense. If you look inside of this, you will not see that. Okay? Yes, there are preamps and things like that in there, but this is very much a computer and very much digital. And what we mean by that is whenever I put a signal on the input of this scope, it's not going to go through a vertical and horizontal amplifier that creates the trace on the screen. This trace is nothing but a computer generated graphic. It really is. There's not a sweep. In other words, if I do this and I slow it way, way down and go way down, you can see it's a computer generated graphic. There's no dot, there's no trace, there's no sweep. This is just a computer generated graphic. And if you notice, it's rolling past in one continuous line. Okay? If you saw our other scope, there was a little dot that just kept going back and forth. You're not seeing that on this. The reason being is that this actually will take a sample, a digital sample. It will take that analog signal that you're applying to the input of the scope, and it will turn it into a digital signal. Okay, so I'm not going to get into all the details of how A to D conversion works and all that, but just understand that it takes that analog signal and turns it into a digital signal that can be read into a computer as a digital word. Okay, and then that digital signal is turned into a image that represents that waveform. Okay, so I have the same signal generator with the same signal that we were looking at on our other scope. Okay, and if we look right here, okay, you can see it looks very much, other than the trace being yellow instead of green, it looks very much like the signal we were looking at on our other scope, right? But it's not. Okay? One of the things is, this is taking this signal, it is taking a digital picture of it, just like your digital camera, and digitizing it, and then it is rendering an image that represents that waveform and outputting it to that screen. So what you're looking at here actually is a computer-generated graphic in a way, okay? It's not an actual sweep as per se. Now, there are some drawbacks to that. So for instance, if I look at, and there are a couple of fantastic videos, the EEV blog and a few other places will actually have on this. But when we zoom in here on one of the things that they're advertising, you can see how this says 2.5 GS per second, and it says 300 megahertz. If you look on the analog type scope, it tells you 400 megahertz, but there's no mention of GS per S, okay? You see that? And what this is it's telling you how many little pictures per second this thing is taking. It's actually capable of taking up to 2.5 billion samples per second. That's what that is, samples per second. So what the heck is a sample per second? Okay, let's look at this. Let's get some paper and draw it. I'll show you. Okay, so what we're looking at here is a very poorly drawn representation of that sine wave that we were looking at on the scope earlier. And on our original analog oscilloscope, all that happens is that trace starts to sweep. You know, that little dot starts to sweep from the left to the right of the screen. And then on the vertical input, as the voltage changes through that waveform, the dot follows it, right? And it draws out this little pattern on the scope. And then it just keeps repeating itself over and over again. What happens with this digital oscilloscope, okay, is as this is coming in every so many times per second, okay, and with this scope a maximum of 2.5 billion times per second, I'm taking a little measurement here and all the way across from this part of the screen to this part of the screen as it's sweeping, as time is progressing. Every period, 2.5 billionth of a second, every that often, it's going to take a little measurement of the input of that waveform, okay, of that channel 1 that we're in, okay, of our vertical. And it's going to make a chart of how many volts that is, or how many digital bits that is, because remember, we're taking that analog voltage and converting it to a digital word, right? And then after we take that gigantic sample, okay, all those different measurements at each point, then it's going to turn that into a representative waveform and print it out on the screen. Now, the more samples per second that an oscilloscope can handle, the more accurate this is going to be. So for instance, if this scope had less samples per second, this would not be as crisp and clean of a line, as it is with the higher sample rate. So high sample rate is one of the functions that you want to look at. And that's the difference between a really cheap scope. You know, some of those, $20 little build it on a little circuit board thing scopes, their sample rate is very, very low. Okay. And as a result, any waveform that gets too high of a frequency, the oscilloscope is not going to be able to sample it. It's just going to only pick little bits and pieces, and it's only going to be able to show you parts of that waveform. Okay, so in order to have a really clear looking display at a high frequency, a digital oscilloscope has to have a very high sample rate so that it can take enough pictures of this to stitch it all back together and get an accurate representation of the image. Okay, so in most cases what you'll see is the higher the bandwidth the scope is rated for, the higher the sample rate it will have. So, case in point, okay, if we go back to our scope over here and we look, this is a 300 megahertz oscilloscope, and it has a maximum sample rate of 2.5 gigasamples per second. If we go up just a little bit and we look at this other scope, it's only a 100 megahertz scope, and it only has a maximum 1 gigasamples per second. Okay? And the reason they can get away with that is that it's not rated to look at that high of a frequency as the other scope. Now that's not, you know, this is a little bit deceiving, okay? So, you know how we can have two stereo amplifiers and they're both rated at 100 watts per channel. We've heard this so many times. And yet one of them sounds a lot better and has more perceived volume and power, even though they're both rated at 50 watts. Well, that is somewhat true with an oscilloscope. The sample rate is only part of it. There's a lot more that goes involved in the circuitry to actually make that waveform look accurate and look sharp and clear. And the idea is, in a perfect world, when we have a digital sampling oscilloscope like this, we would be able to, this trace should look exactly like an analog scope. And as you notice on this one, it does. And actually, within the specified range, this lower end scope does the same thing. I mean, it has just about as good of a trace, and we'll see that here next. Okay, but I want to get more into the functionality first. Okay, so the first thing we're going to do is go over some review, because I'm going to show you the similarities with our analog scope so that you can understand that really in most instances an oscilloscope is an oscilloscope. Even though we get newer and we get more modern technology and things get fancier, we still have the same, we're looking at the same thing in the same way. So if we go over to here, and I'm going to disconnect this so that this wire isn't in your way, and we zoom in a little bit, we still have vertical and horizontal and trigger. You see them? And even though this is a digital oscilloscope and all these fancy things, it's still the same thing in a way. Now, this is a 2-channel scope, but if you notice, there's only one vertical control. And the reason being is I don't have 2 separate vertical amplifier sections. I don't need them because this is a computerized oscilloscope. It's digital. So really all we need is these 2 buttons. And by pushing these buttons, we can toggle between channel 1 and channel 2. So if I want to control the vertical of channel 1, I push the yellow button. If I want to control the vertical of channel 2, I push channel 2. And you can see channel 2 shows up. It's a blue line, and the blue matches the blue button. So everything's color coded. And this is not an actual pot or an actual switch, but it's actually a rotary encoder. It's an optical encoder knob. And the computer monitors that encoder, and it changes the data. Okay? So, this is much more like running a computer than running an oscilloscope. Even though they've tried to ergonomically make it mimic an original authentic scope, behind the scenes is very different than what you see on an old analog scope. So as I turn this knob, I'm still changing my volts per division. So if I go over here and I look here, I'm going to turn channel 2 off so we're not confused. I'm at 500 millivolts per division. Very, very same thing that I had on my other scope. And if I rotate that little rotary encoder, I go down or up in volts per division. Also, if you look at the little connector, it's a little bit different than our last oscilloscope. And if we look at the probe, it's the same. It still has the little pin. You can see the little pin. Okay? But if you notice, the little ring around that connector has all kinds of different contact areas. And if you also notice, this is kind of shaped like a key. That's because there are newer, more modern types of probes and attachments that can be plugged in there. Like Tektronix has differential probes that are basically, they're smart probes that can help the machine set the display up to match what that probe was designed to measure. But these old probes are backwards compatible, so I can still take this probe from that 2465, and theoretically, if it'll fit, I don't know if it will because of those tabs, I should be able to put that probe in there. Nope, this one won't fit. And if it weren't for these little wings here on the end, I could plug that in there and it would still recognize it as a ×10 probe. This Probe Master universal Tektronix probe with the little pin, it will plug into the 2467, it'll plug into this scope, and it will plug into the 2465, and all three of them will recognize it as a ×10 probe from that little pin. But these other contacts allow you to use even yet more different types of probes, okay, special ones that we're not going to talk about yet, but more functionality, okay. If you notice down here, these newer scopes have a USB flash drive, and that's for, you guessed it, this machine's a computer. It boots up like a computer. It has software in it, and you can actually upgrade the software. You know, just like you can upgrade your computers from Windows 8 to Windows 10 or Windows 7 to Windows 8, whatever, you can upgrade the version of software on your scope. Every once in a while, Tektronix will release an update for the software, and you can download it from the internet and load it onto a USB drive and plug it into there. You can also store things, measurements and settings and all kinds of things from the computer onto an external drive like that. And not only will this scope do it, but if I look up here, even the lower cost scopes can do this as well now. So that's one of the really neat functions of these newer scopes. The fact that once you get the knobs the way you like them, there's actually a way to save those settings. So you only have to do it once, and you can recall those settings, and all the knob settings will come back to where you saved them. On an older scope, every time you want to set up that setup, you have to go turn all the knobs until you get it to what you want, get it set the way you want it. Okay? Now, why would that be important? Well, I have some employees that use the oscilloscope occasionally, but not all the time. And there are certain pieces of equipment that we don't work on very often that require you to set up your scope a very specific way to monitor the waveform. And every time, in the old days, they would have to call one of us older guys or more experienced guys, and we'd have to walk them through, turn this knob, set this, set that, set your trigger to this, set your delay to that, set all these different things. And now that we have these newer scopes, we set it up one time, we save that setting, and all they need to do the next time they need to do that is go in and recall that setting, and the scope sets itself up. So that's wonderful. You can have a setting for maybe testing AM radios, let's say. I'm just giving you some examples. And then a setting for when you want to measure an IF section of an FM radio, and you can have another setting saved for measuring the multiplex signal in a scope or in a radio, and you can have those all set as different settings. So for instance, I can go to Save Recall, and I have a little picture of a floppy disk for those of you who remember what those are. And you can see here, I can have several screens full of them. I can have up to 10 of those. I can have up to 10 different stored settings. Okay? And it even shows you here Okay, you can actually look what's saved in there. Okay, it's a computer. Okay, it is a computer. So there you go. These are things you're not going to see on an analog oscilloscope. If you go onto eBay and you buy an old Tektronix 465, or you buy an old Hitachi scope, or a Leader, or an Ico, or something, whatever you buy, and it's an old analog scope, you're not going to see things like this on those. Now, some more similarities. If I go to this menu button, okay, and this is you're gonna see these general controls on every digital scope. So we're gonna look at the other scope above this one here in a minute, and you're gonna see that it's almost the same layout as this scope, even though they're two different manufacturers, two different price ranges, everything, same kind of general layout. So you're gonna hit menu, and now you can see on the right side we have our coupling. Remember how we could change between AC and DC coupling on our scope? Well, now we do it through this, and it will react the same way as if you have AC or DC or ground coupling selected on the other scope. If you look down here, there's a symbol of ohms, and you notice 1 M for 1 mega ohm or 1 million ohms, or 50 ohm. So just like the other scope, we can have 50 ohm termination on our input probe, on the input of our probe socket. Okay. These scopes even have protection on the 50 ohm. If they sense a higher voltage than what this scope is rated for, it will automatically switch 50 ohms off and switch it to the 1 mega ohm impedance to protect the input of the scope. Okay, so there's a little bit of protection. Even the 2467, I believe, has that in it, but some of the older ones that have that do not, and you got to watch that or you'll damage your scope. All the little settings for, you know, inverting, so we can invert. So you can see along the bottom on this scope, these buttons select the sub menu, and then the right hand side buttons are the ones that show you the actual items within that menu. So if I have the invert menu on, I can have the signal inverted or not inverted. And if you recall, just like the other scope, if I want to invert the image, and you can see it just flips it around, see? Okay? There's reasons why we may want to do that. Okay, we'll get into that later. Usually you don't have to mess with invert unless you're looking at a negative going waveform and you just want to look at it similar to a positive, or if you want to use two different probes, you know, two channels in differential mode, and I'm not going to get into that right now. So you have invert, bandwidth. Okay, you can actually make this oscilloscope be similar to a 150 or a 20 or a 300 megahertz scope. Okay, there are some reasons that you may want to do that, because you may want to reject higher frequency signals that may be riding on that lower frequency. We can change that by changing the bandwidth of the scope, and by changing the bandwidth of the scope we change the sampling, and it does several different things. Okay, again, digital scopes can do things like that. Fine scale, if you notice, whenever I turn this knob, it changes it in a certain way. See, 1 volt, 500 millivolts, it makes pretty big jumps. Okay, but if I go to fine scale, I can use my little data wheel and I can change it any way I want, so that when I turn this knob, it moves my scale by whatever amount I set it to. Okay, that's an advanced function. Most people never use that. If you had a very specific circuit you were testing and you wanted to be able to make those adjustments, this scope lets you do it. Even the cheaper ones that are digital let you do that sometimes. Okay, position, okay, And again, you can have things, you can have offsets and positions, and what that does is basically it will change where your zero is with respect to your arrow, things like that. Again, functions you're most likely not going to use unless you're on a laboratory research and development, you know, you're designing circuitry and you need a very specific setting. Probe setup. This allows you to make adjustments to the individual probe that's plugged in, okay? Or you can manually adjust what you want the input port to mimic. So it knows that I don't have a probe plugged in. It immediately defaults to a ×1 probe or a ×1 signal. So it is what it is. You know, it's not doing any kind of math to that input. But I can manually tell it to set it to ×10. So let's say I have a non-Tektronix probe, and that probe does not have this pin to, you know, that's automatic sensing, but it's still a ×10 probe. Well, I would have to go in here manually then, if I want it to display properly, and tell it that that is a ×10 probe that's in there. Okay, so this allows you to manually do that. Okay, so different things you can change, voltage or current probes. There's all kinds of things that this scope can do that the other one didn't from a digital standpoint. Okay. Same thing with our horizontal. We have an encoder wheel. We still have our vertical and horizontal position knobs. Okay. Same thing. And we even have a little magnifying glass, which is a really neat function. Let's say I'm looking at a signal and it's a really high frequency signal. If I hit my magnifying glass, see the little box? That little box that I can steer around in here, okay, with the knob, that little box is now spread out in this whole width of this screen below. So it's a quick way of looking at a waveform and looking at a magnified view of the waveform. Okay. Again, something you can do with a digital scope that you will never be able to do on an analog scope. Okay. Now, we also have functions up here in the corner, which once again are very, very exclusive to digital scopes. For instance, the display. If I go to the display, I can make this have a persistence to the screen. Okay, so if I turn persistence and I go persistence on, and I put a waveform in there, and I move the waveform around. Let's see if I can change this. And you can see I can give the scope persistence or lag. So if there's something that shows up real fast and goes away real fast, I can use that persistence to be able to see it a little better. Okay, there's other ways on these scopes to do it, but in the old-fashioned oscilloscopes, they had what was called P scopes or persistence scopes, and that's how they did it. This mimics an old-style persistence scope. Okay, you can set it back to auto and turn it off and get rid of that. So you can do that. You can adjust the backlight intensity. So you can see I can make it, I don't know if the camera's picking that up, but I can make the background brighter or darker. Graticule, I can change the graticule. Now on our scope over here, this is actually a stencil, you know, it's an overlay, and those black lines are actually stenciled on there, painted on there. But this is a digital display now, and these graticules are actual a picture of a graticule. They're not a real graticule. So I can make my graticules look with or without the center crosshairs. I can put the crosshairs without the graticules and just have dots, or I could just have a straight frame. If I just want to look at a waveform and not have the graticules in my way to measure, I can do that. Okay? So it lets you do all that. XY. We talked about XY mode a little bit on the older scopes, where channel 1 is going to affect the vertical and channel 2 becomes your horizontal, and you can make those Lissajous patterns. Again, we have all kinds of different ways to adjust that, so we can set that. Okay, so that's how you can do XY mode. Okay, and we can change the color palette. So right now this is a full color oscilloscope, but I can also make it look monochrome if I want. Okay, and both of the traces will be the same color. Okay, so many different things that you can do with the display on it on a digital oscilloscope. Okay, another advanced function. Now our scope up here, our 2467, actually has some of the basic functions of the cursors, but the older ones don't have anything like this. Okay, it's, you know, usually you see this on digital scopes. So if you look up here, there's a cursor button, and if I press it over here, you can see we can now measure things. Okay, so I can take the horizontal bars, for instance, and if I back you up just a little more, this data wheel, okay, you have select and then coarse and fine adjust and then the adjust. And what I can do is I can move my first line to the top of the waveform, hit select to select the other line, move it to the bottom of the waveform, and if you notice right here, it gives me the distance in volts of those two lines. So it's actually a way to measure my waveform. You can see that's about 2.2 volts peak to peak right now. Okay, and conversely, I can also hit vertical bars and I can measure the time of a waveform. So I can take my first cursor and move it right there, take my second cursor and move it to, so for instance, I can go from this zero crossing right here, okay, and I can go to this zero crossing right here, and you can see I have a 200 megahertz waveform on there, and look, it says 200 megahertz. Or 200 kilohertz, I'm sorry, it's a 200 kilohertz waveform. So I no longer have to count graticules and look at my scale and calculate it on a calculator or in my head. I can just use my cursors. Okay? So that's another function. Now, again, some of the other analog scopes have that basic function, the later ones, just before the digitals like this came out. But generally they don't. Okay? Now, here is the coolest part of a digital scope. In my opinion, one of my favorite things. If I hit this MEAS, that means measure, and you can see a menu comes up, and it's a measurement menu. Look at all the things I can measure. I can measure the period between one cycle. I can measure the frequency of a waveform. I can measure the delay between two pulses. I have 6 screens full of measurements. I can measure the rise time, the fall time, duty cycle. You know, if I'm looking at a pulse width modulated circuit, I can measure the duty cycle. Positive and negative pulse width, burst width. I can measure phases if I'm looking at a phase angle of something. Overshoot, I can measure peak-to-peak voltage, which we did with our cursors, but this will automatically place the cursors. So if I measure peak-to-peak, it automatically tells me my peak-to-peak voltage right there, 2.2 volts. See that? Very cool. I can measure the amplitude. Okay, so there's the amplitude. I can measure the peak, the high peak and the low peak. I can measure maximum, minimum. I can measure RMS value. If I want to measure the RMS voltage of something, I can hit that. It lets me only have 4 measurements, but I can do indicators off. Okay. And so you can see all the different things you can measure at once. So, very cool. So, for instance, if I were using my dummy load and I wanted to measure the true RMS voltage without using my true RMS voltmeter, and I wanted to look at the waveform and measure it at the same time, I could do that, and then I can directly calculate my RMS value from there and figure out how many watts the amplifier is. Okay, so that's pretty cool. So there's a whole lot of things you can do, and this is just scratching the surface of what you can do with an oscilloscope, with these digital oscilloscopes. Another thing is, let's say we have an unknown waveform, and this thing looks like that. It's all messed up, and I don't really know what it is, right? We have the get out of jail free card called auto set. See that button called auto set? All I need to do is press that auto set button, and you can see it automatically sets the volts per division. It sets the time per division. It sets the trigger. Everything automatically to give you a good looking waveform. Now you can change it from there, but that'll at least get the waveform popped up on the screen. Now auto set really only works with a steady waveform like this. If you have a like a complex waveform that's moving and chasing, it won't always lock in. But for something like this, it works great, especially for somebody not familiar. Beyond that, on this scope, but not on others, there's a little door that opens up here, and you can plug modules, and those modules give you additional software functions that the scope can do. Okay? The other thing you can do is math. So if you look down here, you can do math, and if you hit right now it's set to look at fast Fourier transform, FFT. Okay? And you can see, you can look at dual waveform math if you're looking. You can add 2 channels, subtract the difference between. So if you have channel A and channel B together, the math, the red trace, will be the resultant of whatever you have set there. Okay? So this is this signal plus this signal equals the red signal. Okay? And it's showing you that. And you can change it to times or divide or whatever you want. Okay? Very cool. Or you can even do advanced math, which I'm not going to get into all that. Okay? So you can actually do all kinds of different calculations with that. Now, if you get into some of the even newer scopes, the latest thing is now to have computer interface, where they actually have a software application you load onto your PC, and you plug a USB from the scope into that, and you can control the scope from your from your computer. You can even put the display of the scope up on your computer monitor. So many different things you can do with a digital scope. So that gives you a little rundown on the difference between the analog modern scopes and the full digital modern scopes. Alright, since the last little clip there, it's been about 5 days, and that kind of tells you how how crazy things get here sometimes. So I'm going to try to remember where I left off on this. It seems like we were just getting ready to move up to the low cost scope. But one thing I did want to go over before we go any further is I would like to connect back up to this scope down here. And I want to talk a little bit about the trigger as you compare it to the trigger that we were looking at on the other scope, you know, the Tektronix 2467. Because this trigger is kind of cool, and all the newer scopes work this way, so it's actually really kind of cool. If you look here on your trigger level, okay, now that's very similar to the 2467, the older style scope. You still have a trigger level. We still have noise reject, okay, so we can go into the menu and we can look. We still have the coupling, okay, so let me zip in a little bit here. So we still have coupling, all right, and we can have the DC, the high frequency, low frequency, and noise reject. We can change the slope to trigger off of a rising or falling slope, just like the other scope. All right, I'm making rhymes here. We can also do what's called auto or normal, which once again our older scope had that as well. And so right now it's set to auto, so even with no signal, the scope will continue scrolling through. All those things are the same. We can also change the type of triggering, which is something that we didn't have on the other one, where we can trigger off of a logic signal or a pulse signal or even composite video. If you notice video down here, so when you have a triggering off of video, it actually is looking for the sync pulses of the composite video, which we're not going to get into that today. Once again, that's more than a scope video. That's more about how video itself works. But just so you can understand, this scope can trigger very stable, can make a very stable waveform when you're looking at composite or NTSC video. All right. So, anyways, we're going to leave everything how it is, but I did want to show you one thing, and that is when we adjust this level, if you notice, a little cursor and a little line appears, and it's graphically showing you actually where the trigger point is. So in other words, if we're set to, for instance, right now we're set to looking at a rising slope, and we're using DC coupling, what that is that little arrow is telling us is if we're at 500 millivolts per division, when we do a rising slope, when we hit 1 graticule, which would equal 500 millivolts, that's when the scope will actually trigger. So if we turn on our waveform, and you can see, set our frequency, we can adjust our trigger level, and you can see the edge here, see the little line, and you can see that line is telling you where the trigger is beginning. So if you notice, if I set this arrow to be at this peak, the trigger will start at that peak. See there? Now once we get beyond that, it starts to lose, see, it loses sync because it no longer, since the signal never moves up to that trigger point, the scope doesn't know when to trigger and lock in on the signal. If we come back down into the signal, you see how we can do that? So it's pretty neat. So that's another thing. Now, of course, the other scope can do the same thing, but this one will graphically show you where the trigger point is, which on these newer scopes I think is really cool. Triggering, I know I'm talking about it a lot here, but it's very important when you get, especially when you have a complex or unstable signal. the trigger is what's going to make the difference between you seeing the waveform and not seeing it. So that's kind of why I'm talking about it. Now, there are many other little features that we can talk about with oscilloscopes, but for this particular video, I just want to stick to that. I'm kind of just trying to explain the different types of oscilloscopes and you know, the basic, how to do the same basic thing on the different types that you may see. Now, what we're going to do now is we're going to kind of compare this scope when it came out. It's getting old now, as far as, you know, the models that are out currently. But this was a $7,000 oscilloscope in its day when it came out, roughly somewhere in the $7,000 range. And I'm sure you can find them cheaper and more expensive depending on the source you purchased them from at the time. But I think that was roughly the list price on these. I'm pretty sure, if I recall. But compare that to this little Atten scope, and you know, don't get hung up on the name on this. This particular model of oscilloscope, believe it or not, has been produced by the same company in China, and it's been released under many different names. Atten is one of them, who no longer carries oscilloscopes, I don't believe, but I think Siglent is another model. I forget the other. There's 3 or 4 different manufacturers that I've seen this exact same scope. And there's really no difference other than the name on the front. Even the firmware from one and the other a lot of times will load and work properly. Actually, this has the latest version of firmware from Siglent loaded on it, even though it's an Atten scope. So if we look here, I'm going to shut this channel off, go back to one division. You can see, or one channel, you can see that this is a very similar looking waveform to the one that we were looking at on the scope down below. Now it's a little bit more jaggedy, okay, not quite as clear. If we really zoom in on it, you can see that if you remember on that other one, the line was very, very distinct looking. And if you look on this one, it's a little bit choppier. But once again, that's your sample rate. Okay. The other thing is, you know, the screen on this isn't going to be quite as reactive or as responsive as the more expensive one. But really, for what you guys are going to do, what most people are going to do, you're really not going to see a difference. This scope basically does the same thing. So really, these oscilloscopes are going to be very similar to one another in what they do and in what you can do with them. Now, you know, this is not going to be built to the same quality as the more expensive Tektronix, obviously. You know, the connectors are going to not be as, you know, as secure. There's going to be more plastic inside. You know, things can work loose. But honestly, I've had this scope actually started out its life with one of my service engineers out in the field, and we serviced a lot of x-ray equipment with it, and it worked perfectly well. It just started to have some problems with the firmware, with the triggering, and so we replaced the scope, and this one kind of sat around, and then lo and behold, I found out that Siglent had released a firmware patch for it to upgrade it, and I loaded it in there, and sure enough, it seemed to correct that problem. Now, as you can see, as we've been talking, that waveform is kind of creeping along there a little bit, and you can see even with me, you know, setting the trigger, it doesn't hold very well. It does, you see it drifting a little bit. Now that doesn't hurt anything when you're just measuring a waveform and so forth, but it creeps a little bit. And that's just kind of the way these scopes are. They're not perfect, but they do work. They work pretty well. So as far as the knobology is concerned, the main difference, if you look at this, instead of having, you know, when we go down to this scope, you have one vertical knob, and you use the two switches to toggle between the two channels. If you look at this one, you have two vertical knobs and a horizontal, and you toggle between them by pressing, you know, this button or this button. If you press it again, it shuts it off. So if I hit this button, now I have two channels. I hit it again, it turns it back off. Hit menu off, same thing. It has the soft keys. It has the USB port, just like our Tektronix. Same thing on your triggers. Once again, we can set the type of triggering. Same thing, edge, pulse, video, slope, alternate. Okay, so different types of triggering. We can select the source that we want to trigger off of, same way. So, oh, and that's why it's rolling right now, because the source is set to channel 2. Now we go into channel 1 there, now it'll lock. So that's my mistake, guys. So there you go, it's locked and it's not drifting anymore. Rising and falling slope, mode, we can do the auto and the normal, again, the normal trigger, where it will only trigger when a signal is present. Or we can do a single shot if you're looking at just capturing a pulse. Remember, these two scopes here are digital oscilloscopes, and they're even called digital storage oscilloscopes because they can actually remember the last thing that they saw. So for instance, if I set this to single, there we go, you can see the little red light lit up and it said stop, because it's already triggered once. And now I can disconnect this connector altogether, and you can see it has captured and stored that waveform. Okay, the Tektronix down here, the 3032, can also do that. All the digital scopes that are out there have this capability, which is great. You know, the old analog oscilloscopes don't have that function, so you can't do that. So there's an advantage if you buy a newer scope over the older ones. Okay, if I hit run, it's going to sit there. It's armed now, and it's waiting once again for a signal to come on. And if I connect this real quick and then off, you can see it's stored it only stores the first one sweep is all it can store. See there? And if you notice, see all that noise there? That noise is actually the noise of the connector not making good contact with the jack. Okay, so that's what you're seeing. Now, this is a really good example of what I'm talking about with sample rate and with these LCD scopes and so forth. If you look really closely, that's noise, but really it actually just looks like individual lines on there. If you were to look at that noise on an analog, you know, high bandwidth analog scope like the 2467, those would not look like little lines like that. You would actually see all the little fuzz and all the little noise in between there, and you could even expand it out and look at the individual noise waveform. Okay, whereas on these digital scopes, unless you start getting into the high sample rate, more expensive scopes, you won't see this. Now, once again, don't believe that just because the 2032 is an expensive scope, it's automatically going to always have a higher sample rate. As a matter of fact, if they made this scope in a 300 megahertz bandwidth, which they may, I don't remember, I don't know, I never looked, it would have a 2 gigahertz or 2.5 gigahertz gigasample per second sample rate as well. So you can't always go by that either, but some of the cheaper scopes you have to watch. There are 100 megahertz scopes out there I've seen that have had lower sample rates, and as you get to the higher frequencies, it really starts to look blocky. You know, you don't see a real clear waveform. So, you know, I'm just trying to give you a few different things to think about when you're choosing a scope. On the lower cost, and by the way, I don't think I mentioned it, this particular scope probably sells for anywhere from $250 to $300. You can pick these up online, eBay or whatever. And even if you're just going to do some basic radio work, with AM and even FM, 100 megahertz, $300 scope like this probably will get you by just fine and work just fine. And now, if you want to do the middle step, if I was going to have 3 of them going from the most expensive to least, I'd have another one stuck in the middle there, like the Rigol, okay, R-I-G-O, or Rigol, R-I-G-O-L, however you want to pronounce it. And they're kind of, there's several brand names in that range. I'm just using that one name as an example. And they can tend to be a little bit more mainstream, a little more popular, more common, a little better supported. And they're at a price point that's they can be more expensive than these and less expensive than these. So they'd kind of be a middle range one. Again, if you're a beginner, I would highly recommend, and I'm not going to tell you what model or what make to buy or not to buy, but one piece of advice I would give you is don't spend money, big money on a really expensive scope if you're not familiar with oscilloscopes and if you're not experienced in electronics. If this is just a hobby you're starting out in, start out with something like up here, in that $200 to $300 range. Don't get the little $30 or $50 pocket scopes or any of that. Those are going to disappoint you because they can't do. Most of them are very low bandwidth, very low frequency, really bad laggy screens. They're just not good. Get a real tool like this, but don't spend big money, because as you develop your skills and as you find more and more of the things that you like to work on or that you're going to work on, you'll start to gravitate towards certain functions and features that suit you personally. And that's going to help you make your decision as to which oscilloscope to purchase. I just showed you 4 different generations of scopes, starting with the old vacuum tube one. And unless you're trying to go nostalgia, and some people do that, even though there's so much better out there for the same or less money, there's an argument for getting one of those really old vacuum tube oscilloscopes like we worked on, like that DeVry, in that if you really wanted to have the experience of servicing old equipment the old way, that's a hobby. People enjoy doing that. I mean, some people set up a separate bench just to be able to have the nostalgia of working with the older test equipment like that. So I'm not going to say don't ever buy one of those. There's a place for it. Some people grew up with these analog, really high performance analog scopes, like that and like that, and they can be had for, sometimes you can get them $50 online, $100, and if you're not looking at stored waveforms, they're fantastic. There's nothing sharper than a really well calibrated, good condition CRT oscilloscope, like the Tektronix 2467s, the HPs of that era, very good equipment. HP, Rohde & Schwarz. There's lots of, Hitachi made some really good ones. Even Hamegg and a few other companies have made really good analog scopes, and you can't discount them because they really work very well when you're dealing with RF and radio and things like that. If you want simplicity to be able to store setups, and you want to have bright, big color screens, I mean, you look how large that screen is on there. I mean, that screen is, that's like a 6 or 7 inch screen, and then you look at this little screen. This thing's only about a 4 inch screen. So much bigger display. It's a color display, so when you're looking at two channels, they're two different colors. So you can actually look at two different, the two channels. You can differentiate channel 1 from 2 from just by the color of the trace. You can't do that on a monochrome CRT. So once again, it really comes down to what you are going to do. All of the scopes will serve you well if you buy one with the right bandwidth, and that's really the biggest thing. If you plan on looking at, at high frequency, make sure you have a scope that can cover that frequency. 100 megahertz scope for most people is more than enough for what you're going to do, unless you're going to get into radio big time, or some digital electronics where you're getting into really high frequency and things like that. Then that's where you're really going to want one of these, because working with digital, you're going to have to capture things that are there and then gone, pulses. You're not going to do that on these old analog scopes. You need a digital scope. So there again, if you're going to work with digital electronics, you want the more modern digital scope. And if you're going to work with like computers, like high frequency stuff, you want a high bandwidth scope. There's scopes that go up into the gigahertz and can cost tens of thousands of dollars. But a basic 100 megahertz scope to look at radios or look at power supplies, for ripple and things like that, any one of these would work fine, as long as you got the bandwidth that can handle it. And like I said, if you're just going to work on AM radio, or you're just going to look at IF on FM radio, even a 50 megahertz or 60 megahertz scope would work. Okay, but for the difference in price today between this, which is 100 megahertz, and this same one, which is a 50 megahertz, not a very big price difference. So, maybe get the little extra 100. But again, don't go buying one of these big high dollar scopes right out of the box, because I know some people say, I just want to spend the money once. The problem is, yes, you'll have an excellent tool. It'll be a great piece of test equipment. It will last you your whole life. But then you spend that money and you realize maybe maybe the Keysight or HP, whatever you want to call them today, or the Rode and Schwarz is a better scope for what you like or prefer, or the Rigol, than the Tektronix. And you've already spent your big money. It's kind of, now you got to worry about selling it or returning it or whatever. So start out on a cheaper scope. Learn it. The only way you can learn this, I can make another 10 videos like this and spend another 10-15 hours on these videos. And if you don't get your hands on the scope and start using it and start looking at some of the things that we just showed on here, you're never going to learn how to use a scope. Okay, that's the biggest thing to remember. So I hope this video helps you guys out a little bit. I hope it gives you a little more education on the different types that are out there. And remember, you always have the comment section. You can message me or whatever if you have some further questions that I can answer. Probably the next video I'm going to do after this is another Q&A. It's that time of month for me to do it. It's been about a month since the last one, and I got inundated with comments over the last 30 days. So it's either going to be a really long video, or I'm going to have to really pick and choose, and that's going to be difficult because I had so many really good questions and comments this last month. So we'll see what it turns out. If I have time, I'll try to put some time into a good Q&A video for you guys. And if things get too busy, I'll try to edit it out and maybe do a little follow-up later or something. We'll see. So I hope this turned out to be what you guys were expecting. If not, let me know in the comments. We'll do a follow-up. And I'm going to call this video here at the end. And I want to wish you all peace, joy, and happiness in your lives. Hope everything is well with all of you. And remember, don't keep the faith, share it with others. Thank you all for watching. Bye-bye.